Good afternoon, DEFCON. I'm Agostino, aka Vanish, and I'm here to talk about slaying dragons. Not the mythical one, so we are not talking about the Hobbit, but we are talking about the one that got modern software through sophisticated virtualization-based obfuscation techniques. This is the agenda for the next 45 minutes. We are going to start with a brief introduction. We are going to see the VM protection evolution. I'm presenting the VM DragonSlayer architecture, and we do a deep dive. We do some live demos, because it's cool. We analyze some performance and validation, and we analyze the limitation, the future work, and the community that I hope to build around the project after this talk. Let's set up the expectation. Why VM protection is winning the arm race. This is what we are going to analyze today. How VM DragonSlayer, that is the framework that I'm presenting today, defeats this protection using hybrid analysis techniques. We do some live demos, as I said before, and also after the talk, the entire framework will be completely open source to everyone to use it. The talk is aimed for malware analysts, reverse engineer, incident response, incident responder, security researcher, and frankly, anyone who is tired of being defeated by obfuscated code or is trying to build better obfuscated code. So before we jump into the technical meat, let me introduce myself. I'm a security researcher with over 15 years in red teaming, Linux and Windows kernel exploitation development, incident response, and reverse engineering. I'm the author, the maintainer of the project that I'm presenting today, or another project that is on active defense that is ahead. I'm also the maintainer of Spiderfoot today, or a fork of Spiderfoot that is being revived, and the Leviathan framework, that is the framework for exploitation, for ABPF exploitation that I'm going to present tomorrow. My research focus is everything that's weaponizable. That's it. And when I'm not breaking things, I love scuba diving because I love the exploration. I'm also the proud owner of 3 cats. And while I'm speaking, they are probably planning the world conquest. That's why they are looking at us. Now, how many of you have ever tried to reverse engineer software protected by VMProtect, for instance, or encounter custom VM-based malware that made you question your career choice? I know some of you have done, otherwise you'll not be here during this talk. We all have been there, staring at assembly code that looks like it was written by an alien civilization having a particularly bad day. Let me show you what we are dealing with. This is what happened when a simple 3-line function gets the VMProtect treatment. On the left, we have an elegant readable assembly, a basic function that any first-year computer science student could understand. 3 instructions, easy. Load 2 values, add them, return the result. On the right, we have what I like to call the algorithmic nightmare fuel. Over 500 lines of deliberately obfuscated code that will make Lovecraft proud. This isn't just obfuscation. It's a complete architectural transformation. But there is what makes it truly nightmarish from a technical perspective. Behind those 500 lines, we have a constraint satisfaction problem with over 1,200 path constraints, more than 256 virtual registers, 64 custom VM handlers that implementing a unique instruction set, dynamic taint propagation across more than 47 execution paths. That's what we have. And if it was not enough, a symbolic execution that challenge that will break traditional analysis engine. The original control flow it's gone. Poof. It's been completely destroyed, and it's been replaced by custom virtual machine. The data flow, hidden behind constraint satisfaction problems that require advanced symbolic reasoning. This isn't just an academic problem, or something that affects a few security researchers. Let me share some statistics. We are living through an arms race that's fundamentally changing the landscape of software protection. I analyzed almost 300-400 samples through 2024 of advanced threat actors. And the results are striking. 70% of them employ some form of virtualization-based protection. Think about the numbers for a moment. 7 out of 10 advanced threats are using techniques that completely breaks our traditional analysis approach. The success rate of existing tool, less than 15%. This means that 85% of the time, your current tool chain is failing you. Manual analysis time has ballooned to 2 to 6 months per sample. And we are seeing over 200,000 variation per day nowadays. The mathematics are unforgiving. We are losing this war through sheer numbers. But let me trace the evolution that brought us to this special circle of hell. Do you remember the good old days when UPX was the height of the sophistication? These early protectors focused on compression and simple encryption. That's it. You could defeat most of them with generic unpackers or just setting the right breakpoint on virtual alloc or VMProtect. Life was simple back then. We didn't realize it, but it was simple. The typical analysis process was almost ritualistic. Set a breakpoint on virtual alloc and VMProtect. Run until you hit it. Dump the memory region. Fix the import. Celebrate with beer because you're done. And then, in 2010, VMProtect 1.x came out, and everything changed. It was like going from child play to adult playing, to casino playing. The introduction of virtualization marked a paradigm shift. Original x86 instructions were converted into custom VM bytecodes. The protection wasn't just about hiding code anymore. It was about a fundamental architecture transformation. But then we move on phase 3. It's like the MCU. We are going forward. And we got VMProtect 3.x. We got Themida VM. We got Code Virtualizer. Those tools raised the bar even higher. These weren't just protectors. They were more like code transformers engine. After that, we got to phase 4. We got to the next level. And perhaps the most concerning development is the proliferation nowadays of custom VM. We are no longer dealing with commercial protectors that we can study, that we can analyze. We are dealing with malware family that now implement their own bespoke protection. APT groups deploy custom protection scheme that can be analyzed with commercial tools, so they fail us completely. And I've seen nation-state malware with VMs that will make commercial developers jealous, honestly. To understand why this is such a critical problem, Let's examine what makes VM protection so effective. I call it the three-headed dragon. The first head is the abstraction complexity. The original code isn't just hidden. The original code isn't just hidden. It's completely transformed into a custom bytecode that exists nowhere else in the universe. That's frightening. We are dealing with custom instruction set that contain more than 200 opcodes with no documentation, no standards. We got polymorphic bytecode generation, dynamic handler generation, and context-dependent semantics. Let me give you a concrete example from VMProtect. A simple x86 instruction like the move is just one instruction representing one single memory load. From one instruction, we get 247 instructions in the protected binary. This means that we have a 247 to 1 ratio, obfuscation ratio. The VM itself is designed as a fortress. These protectors deploy an anti-analysis arsenal with over 50 techniques. Debugging detection include, is the bugger present? That is the common one. PEP being debugged, flag monitor, being debugged, hardware breakpoint detection, time-based detection, and everything can be actually mapped to understand what's going on and if the sample is running in a safe environment for them. We got dynamic countermeasure that includes self-modification dispatcher that change as you analyze them, code flow integrity check, and exception-based control flow that require symbolic execution across exception handlers. But even if you manage to identify individual VM instruction, understanding the overall program logic require mapping the VM internals to something that should be meaningful. There is where even experienced analysts just give up at a certain point. VM registers don't correspond to CPU register. A VM might have more than 246 virtual registers versus the 16 that we have in the x86 infrastructure architecture, using custom segmentation scheme and VM-specific implementation. That's a nightmare. That's the idea. So when we face this threat, what we do? We try to forge better weapon. And that's what I've done with DragonSlayer. After years hiding these dragons with stone knives and bearskin, I decided that it was time to build a proper dragon slaying weapon. DragonSlayer represents a fundamental shift in how we approach VM deobfuscation. The core innovation lies in the hybrid analysis approach. We use dynamic taint tracking, plus symbolic execution, plus machine learning. And we got an automated VM deobfuscation. Here are some key insights on how this works and why this works. VM must read bytecodes. That's our taint source. VMs must dispatch the handler. And that's our control flow target. Handlers have semantic patterns. That's where symbolic analysis shine. Patterns are universal across protectors. And that's where machine learning do its job best. DragonSlayer is built as a research framework, honestly, with a module, but it's built with enterprise in mind. So it has a modular architecture. Let me walk you through the system completely. We have a multi-platform plugin suite supporting Ghidra, that is the one available today. We have the alpha release of IDA Pro, and we plan to do the same for Binary Ninja. These integrate with a REST API that is built on the server side. The core analysis engine includes the dynamic taint tracking using Intel pin, a symbolic execution with a Python implementation using Z3 and Angr, and a machine learning engine for pattern classification and confidence scoring. We also got some ZPU acceleration support for CUDA and OpenCL, but it's in alpha release so far. So you can make it work, but it's not really stable. The system includes some benchmarking and validation, but also it's CI/CD compliant, means that you can use the framework in your pipeline without any issue, because it's just an API code. Let's deep dive into some of those models. The DTT implementation is built on Intel pin with a custom Python wrapper. Let me show you how this works. The pin configuration uses the custom VM Dragon Taint DLL that is available in the source code. We are not going to cover it in detail because we are needing more than an hour just to go over there. With 300-second timeout, we define taint source as VM bytecode section. Typically, for VMProtect, we got for 4010 to 4050 in the header. The point is, this is the only input that you have to take, that you have to put into the framework. It's the only input that you have to get. Because if you put it too wide, this is going to run forever. Some feature that we have in the DTT includes instruction level precision for memory reads, automatic handler discovery via control flow analysis, multi-threaded taint propagation tracking, and real-time confidence scoring for discovered handlers. And this is just the DTT. This is how it works in practice. Everything is a library, so you can call the entire framework or you can call part of it. If you run it, you have just the taint output, and then the Python wrapper processes it and produces the summary statistics. In this case, for this sample, we have 47 VM handlers discovered in 2.3 seconds, 2,847 instructions, 156 taint propagation chains identified, and we have a 100% accuracy rate for handler entry points. Our symbolic execution engine is completely implemented in Python, supporting Z3 and Angr. The configuration uses symbolic execution with a maximum depth of 100, up to 1,000 concurrent paths. We have a timeout of 300 seconds, and the state merging is usually enabled, but you can disable it. It's just from configuration perspective. VM context modeling include program counter tracking, symbolic values for registry and memory, constraint list, and machine learning guided path prioritization. Path exploration, because you can explore the binary that you have, use machine learning guidance through the path prioritizer with VM pattern weights, priority scoring for an intelligent exploration. Let me show you how it's implemented, the symbolic execution is implemented. The core class initialized with a path prioritizer, execution queue management, and configuration from the VM DragonSlayer config. That is one of the configuration class. The main execution loop runs asynchronously, so it means that it just runs without you need to pull it. Processing the execution queue while respecting maximum path and timeout constraint. For each context, we get the highest priority path, execute one symbolic step, and process result by adding terminal states to completed path and non-terminal states back to the queue. The path prioritizer uses machine learning guided path exploration with VM pattern weights. we define the dispatcher access with a weight of 2.5. The handler entry gets a 2. The VM registry access gets 1.8. The bytecode fetch gets a 2.2. And the anti-analysis checks gets a 3. Our pattern classifier implements a multi-method approach with automatic method selection. The system supports rule-based classification, similarity matching, machine learning classification, and a hybrid approach. The auto-classification logic trials rule-based first because it's fastest. If confidence of the rule base is below 0.8, it tries similarity matching. If that's below 0.7, it falls back to machine learning exploratory mode. The pattern database is back to SQLite. Default patterns that have been added to the platform are, for instance, VM add stack, VM conditional branch, MBA obfuscation, and so on. But that's just part of the framework. We also have the Ghidra plugin. Let's have a quick view of the Ghidra plugin. The Ghidra plugin just shows how you can interact with the framework. So you can define which kind of engine you want to use, which kind of confidence you can set it from the framework. You can get the result view. So you have all the path, all the VM discovered, all the path, everything. And we have statistics over the engines that are running. But let's begin the hunt. Let's see how it works. Let's start with a real VMProtect 3.6 sample. This is a commercial license validation function that contains initially 47 instructions. After VMProtect, it became 2,847 instructions, a 60-to-1 ratio. Protection feature includes virtual machine bytecode obfuscation, anti-debugging, and so on. The manual analysis estimated for this sample is from 3 to 4 weeks. As you can see, the VM DragonSlayer initializes the dynamic taint tracking and launch the Intel pin with our custom DLL. Within seconds, it detects the VM entry point with a high confidence. The handle table is discovered and contains 51 entries. The symbolic execution phase starts from there. And handler analysis complete with 47 handlers discovered and 43 analyzed. We have a roughly 90% success rate. The semantic operation discovered include VM load license, XOR decrypt, string compare, conditional jump, and return value. And everything is done in roughly 3 minutes. The transformation that comes from this process is actually pretty dramatic. The protected version shows thousands online of unreadable assembly. The deobfuscated version reveals the true algorithm. Load license key, decrypt XOR using the key, compare with the expected value, and jump if invalid, return success. Clear algorithm after the process. Just 3 weeks reduced to 3 minutes plus the analyst enrichment time. That's it. Let's analyze the second sample. It targets a real-world banking Trojan from an incident response case. This sample used completely custom VM architecture, and 3 teams completely failed to analyze it over 6 months. VM DragonSlayer in exploratory mode handles also unknown architecture. Automatically, if it doesn't find any signature, it goes with heuristics. The custom VM implementation is discovered with a 64 entry handler table using hash-based dispatch. Bytecode region is 4K of XOR encrypted content, and VM context are 256 bytes, and roughly 60-bit opcodes with variable operands. Everything is being done in roughly 18 minutes. But there is more. The actual framework automatically identifies VM operation and their purpose. This is part of the report that the framework gives you. We have VM load URL that loads the URL from an encrypted config. We have VM hook browser that installs browser API hooks using set Windows hookx and plus DLL injection. We have VM capture creds that extract credentials from browser, Chrome, Firefox, and Edge, in this case. And we have VM custom crypto that implements a custom CRC32 variant that it was never seen before. So it was a good attribution part, technical attribution IOC. The intelligence value from this report is actually immense. The complete behavior profile extracted automatically, the attribution markers in custom crypto algorithm, and we have the TTP that can be easily mapped to the Dmitry attack framework. Everything been done in less than 20 minutes. Plus, the time that the analyst needs to read the VM DragonSlayer report and then reach it. But now, let's see some more dynamic demo. Let me show you what happens if we load multiple samples to the platform and how we handle it. In this case, we have 3 samples that are loaded through API. Those 3 samples are VMProtect based, Themida, and the custom VM. We have the first one that is actually analyzed in almost 3 minutes. And we get the actual handler number and the handler type. Oh. Then we have the second sample, that is the Themida one. Themida is a little bit more difficult to analyze. So we got some details from it. And some of those details are also regarding the handler and all the address of the handlers and how have been used. So we have a DTT, a symbolic execution. Everything is guided through machine learning. The third sample is just custom VM. So we don't have anything. We don't have documentation. We don't have standards. And also in this case, we got some handlers to lift the sample and try to decrypt it, and try to deobfuscate it. But let's see how it works from a statistical perspective. We have performed a complete evaluation, and we use roughly 300 samples over 12 months. Those 300 samples were divided between 15 protector families and almost 50 malware families. Among those, we have 25 nested samples, means VM inside the VM. And this is the success rate of the platform. So we got from roughly 60% of manual success rate for VMProtect 2.x to 84. And we got an overall 70% of success rate from different families. But that's not the point. The real improvement comes from the time. because we went from 2 to 6 months in analyst time to roughly 1 hour. That's the key point. So we are saving analyst time. In this way, the analyst can focus on something that is truly important for the organization. For instance, per sample, we went from roughly $40,000 of analyst time to 50. That's a huge ROI. Let's see some case study in which we use VM DragonSlayer. The case study one involves a financial institution facing a banking trojan. The sample used custom VM plus VMProtect 3.6. The traditional analysis took over 3 months, showed complete failure. We have a partial analysis using Ghidra Pro, and X-ray, the compiler, failed completely. It required 6 senior reverse engineers on the case, means roughly $200,000 in analyst time for 4 months. The VM DragonSlayer took the sample, and the results after 3-hour analysis were 73 VM handlers, 91% of handler classification. We identify 7 novel evasion methods and provide full Ghidra integration with annotated documented binary. Total cost, $150, roughly, plus the computational resource. The technical breakthrough of this implementation includes the finding of a novel browser certificate bypass, never been documented before, a polymorphic VM handler with a 4-hour mutation cycle, and a complete attack chain reconstruction for defensive development. That's the second case study, in which we analyze a batch of state-sponsored generated malware that contain almost 47 implants, developed all with VM protection technology. Traditional approach will require 6 analysts, mostly, 12 to 18 months to analyze everything, means almost $1 million in analyst time. We take it in 1 weekend. So we batch it, we give them to the platform, and in 48 hours, we got a 70% success rate across all the sample. The intelligence breakthrough of this analysis include infrastructure, the campaign infrastructure completely mapped, the code reuse pattern we find across the samples, and also, and this is important, the development timeline was reconstructed from VM evolution over time, because we see how they change over time the implementation of the VM. And this is actually a unique IOC for the specific threat actor. But the platform is good. I developed it, so I can say that. But it isn't perfect. We have a 30% failure rate across challenging scenario. We have complex control flow that accounts for roughly 13% of failure. In some cases, it's really because the sample is too complex or is too annotated. Another things that cause failure is actually the resource constraint. Because sometimes we have individual handler that exceeding 10,000 instructions, deeply nested obfuscation with more than 5 layers of obfuscation. In those cases, it's really difficult to have the resource to handle this kind of computational capability. That's why we are moving over the GPU acceleration part. But also, some novel techniques produce some failure, and including AI-generated or quantum-resistant technology that can generate some failure in the analysis process. But what's the future? The first thing that I would like to develop from here to the end of the year, and I hope that someone will join me, it's a machine learning advancement that include transformer-based handler classification, anomaly detection for zero-day VM techniques, using unsupervised learning. Probably the idea is with 3 sigma deviation threshold. Transfer learning for cross protectors that require, in this knowledge, this transfer knowledge, I hope is going to require 70% less training data. The other thing that I want to develop is an enhancement of the Ghidra plugin to be more integrated with the platform, in which we have a real-time handler annotation that is not there now. You need to do it manually, unfortunately. Automated function naming based on semantic analysis, and detailed commenting with confidence score, but even a cooler feature. The cooler feature is binary rewriting. So you took the obfuscated binary and you rewrite it in clean code. That's the idea. I think it's doable. I didn't have a lot of success with it, I have to be honest, but I think it's doable in an automated way, in which we provide a complete pipeline with full VM structure discovery, handler semantic analytics, control flow reconstruction, and clean code generation. So to conclude, to wrap up what we have seen today, the VM protection actually dominates the modern malware. We have a lot of modern malware that use that. Manual analysis cannot scale. That's why we need automation. And it's not just possible, it's needed. It's essential. Hybrid approach works if you choose the right tool to do the right thing, not like LLM, you use LLM for everything. Open source, I hope, is going to accelerate the process, having more researchers on board that can help develop this kind of technology. Because the defender advantage is achievable if you have the right tool, if you have the right techniques, and if you have the right community behind it. VM DragonSlayer is going to be available on GitHub after the talk, just the time to go back to the hotel. Add these others. This is open source because I firmly believe in democratizing these capabilities. And just remember, every dragon can be slayed with the right sword and the right community welding it together. Thank you for your time. I hope you enjoyed the talk. I'm going to stick around if you want to ask some questions, so I'll be around. Thank you.